And you know, I run Linux, all right, Colgate's not gonna get along at all, so. If you send a couple million, then I'd be happy. I'd do Windows. He hasn't done it, so. But I've been thinking about things. And you can actually source things from the web. Something I've used, but I never really thought about it. So someone asked me what happens. Well, in Linux, you know, if you download something, you know exactly where it is. All right, I'm in a directory. I'm probably in a subdirectory a mile long, but I know exactly where it is. And sometimes if you download things in Windows, you don't know where they are. Really, right? I don't know if something could pop up. But then you'd have to put the path into that directory if you're running out from another way. So I never had that problem in Linux. But then it's dawned on me, we can download everything from the web. All my data files on the web are in HTML, because for a while Windows had the whole time it wasn't an HTML file. So Colgate's always makes it. So, I'll try to do that. Then you can see where things are going. But again, you don't have to run R. I've been running R in class because I can do things much easier. We can do examples much easier than Minitab. But I'll go back to Minitab every once. Okay. So let's look at the Darwin data. There must be a way of reading HTML.
There's a package on HTML.
Okay, maybe I'll look for that. I don't want to know all this. It's just basically mess up stuff. Dot table one. Okay. So let's look at the Darwin data. That's a nice data set. Next, I added Here's the Darwin data, and you have to remember Darwin didn't know anything about DNA. Menno lived the same time as Darwin did, but for some reason they didn't communicate. Well, they didn't have email. They lived in different countries. I don't know if they were even aware of each other's existence. I think they knew. But it's too bad they didn't get together, because they might have put the thing together on DNA long before it was quick and possible. So here's the data. So this is Darwin's experiment on cross-fertilized plants and self-fertilized. So he took 15 pots, and then he planted same species of plant, but in each pot one was self-fertilized and the other was crossed. And we wanted to see if there was a difference in height. Height is important for a plant, right? Because in a sense, it's closer to the sun. That's the one thing plants and trees have to do, right? They have to get to the sun. So the bigger the better. So Well, let's just put the data in on. I use scan quite a bit. And I can skip to that. Oh, that puts me. I can skip that. I got it on the wrong side. So the data then finally. And we just want the differences, right? But let's get the y, let's get the y and cross. Let x be solved. Now, is this a good paired experiment? Well, I mean, it is a paired experiment. That's exactly how we're going to analyze it. But what's the relationship? Well, the plants are not related at all, right? But they had exactly the same environment, same amount of sunlight, hopefully in terms of pots or whatever, and the same amount of water, fertilizer. What's that? Not a very good pair design. It's got 2 hours. Again, it's a plot. So 2 plots that have hours. So the plot is, yeah. These are cross-fertilized, but they must have had bad appearances. Plots 18 and 20. No, I can't do that. You could do box plots too. It's 15 days. God knows what I'm doing. That says it all, right? I mean, you do have these, actually, one of the outliers is there's a big gap. Which is good, right? Because their design wasn't that good. I meant to say I got carried away with the outliers, but it was the, let's go back and do it. See, there's not any strong linear relationship. They are not very important, you just have these outliers. So as an experiment, pairing didn't really help. Okay. Thank goodness he had such a huge gap. Well, we're certainly not going to do it by hand today. Can't do anything. So now we just had D, B, Y lines X. Here's our differences, right? And there's only two negatives, right? You could use a sign test on this. But let's use a sign rank Wilcoxon. And let's get the estimate of the effect out and everything else. So we just want to do Wilcox, right? Because let's do it on differences. Put this thing in so we get the confidence interval and estimate. P-value is 0.04. Okay, so Darwin rejected it. No hypothesis that it doesn't matter if it's self-crossed. Okay, so it does matter. Cross is ahead, right? And we have an estimate of the effect. The estimate is 3.13 units. I forget what they measured in. Darwin might have been using inches. Okay, and the confidence interval goes from 0.5 to 5. Any questions on the sign test? We just take the differences. It's one sample then, and then we just do what we would do for one sample. I use delta, not theta, as a symbol in class because it is a shift. Actually, it's a beautiful two-sample problem, right? Yeah. There's not much dependence in pairs. If that is two samples, wouldn't be that dependent, right? Anyways, nothing's going on but a shift. See, if you draw all these lines, they're almost parallel. It's a very good two-sample problem. The only thing going on is a shift in the page. So some of the pages. Okay, then the other one was a test on independence, and I found my Scottish data, but I found a very good data set when I went later. So let's go with this one. Okay, so now we're talking about independence, right? And last time we did discrete, and today we'll do continuous. And the discrete case was just a chi-square test, right? And this is a very good data set. If you've had me class before, you might have seen this data set. I use it all the time. But this is type of crime and alcoholic status of some convicts, okay? So they're in the penitentiary, and they just went out and sampled, I forget how many are in it, a moment. And so we've got them by type of crime and alcoholic status, and then go that up. It's in column C1 and C2. This is my data. And C1, the first column is alcoholic, and the second column is mild. And the data are arson, The crimes are arson, rape, violence, theft, coining, and fraud. Okay? Those are the roads. So we categorize them as discrete data, discrete random variables, right? X would be type of crime. And those are the categories, arson, rape, etc. And Y would be whether they are drunks or not, C1 and C2, right? So, and we want to test for independence. Okay? I think I have all this. Okay, so this I'll just put in to R and then we can analyze it. I'll just put them in column by column. That one seems to be the way to go. Just call it math, okay? I'll just put them together. So I have the same table I have. Any questions on that? Well, you can't see it.
No.
No questions on that?
Probably the only young thing I understand perfectly.
Yes, anyways, there's the data, right? Now, don't look at it. This is a neat data set because you know how to look at it, no prejudgments, and then let's do the chi-square test. It's best if you put the chi-square test in a variable, so let's call it CHI. So, we just number crunchers today. We don't know what's going on. We do the chi-square test. And the value is 49.7. There's only 5 degrees of freedom. The p-value is 1.5 times 10 to the minus 1. So it's highly significant. So what's going on with the data set? And what you can do is you want the residuals and the expected values. There's a command in R, its attributes. If you're doing many-tab, you win in this one. It'll do a nice analysis. You'll get everything at once, at least you used to. You'll get the frequencies in the categories, you get the expected frequencies under H naught, and you'll get the residuals. And then it'll pump out the test statistic in terms of contribution to chi-squared. So you can see everything at once. And for some reason, R doesn't want to do that. It's in expected and residuals. I'm not sure if contributions are in there. Might be one of those. But you can just do residuals. You know, the residuals, and these are the standardized residuals, which is all right. It's not the raw residuals. But you can see what's going on. You're way off in this. Otherwise, these are about the same. They're very similar. It's the 6th row, right? So what's the story on this data? Well, the 6th row is that last one. And, it's, the story is alcoholics do not commit fraud. Of course, people have told me these are the ones that are caught. These are drunk fraud people that debated this. If that's the story, then what you can do, often that will happen if you're doing a chi-squared analysis on a problem of interest. Often you're going to reject. Okay. Again, it's almost you have this x and y. You think there's a relationship, and you don't reject independence. And then you say, oh, I must not be thinking right. So you often reject. You can do an amateur analysis. Okay. You got to be careful. You're starting to do a lot of tests. You might do one erroneous. Or you could say, I'm just investigating now, and then I'll do another experiment. But it's a simple one to do. You just want to take the data. I just want to take the first 5 rows. So I've eliminated fraud, and then even when you look at the data, that's why I don't want you to look at it too close. They're very similar except the rest. Percent proportions are the same in each column. But if you do if you do chi-squared on just those rows, and it's not significant. So conditionally, if you know they haven't committed fraud, then type of crime and alcoholic status are independent. What would your confidence intervals be in this case? Suppose they wanted a confidence interval. Might could even go across. People committing arson. What if I, just in general, so you had this chi-squared test. We did this chi-squared test, say in general. And, there seems to be a lot of arson in this area. You moved here, I was kind of surprised. It's like on arson, you couldn't catch it. I used to look in the morning. Well, the sampling scheme is one big sample, and then you pigeonhole the data, okay? And it's actually dependent proportions, right? And, here's a schematic to help you remember.
He's alcoholic arson. No.
15.6.
Else.
So this would be the formula. That would be your formula. Now, if you do a lot of investigating, again, you might want to move on parameters, but that. When I teach elementary stat, I always talk about these confidence intervals because many books don't, they like present the test, which you're probably gonna reject. And then they don't do anything else. Many times that's where the fun begins, right? You're trying to find the differences. You don't have that many in here. Okay. Okay, then, so we were talking about the continuousness, and I tried to write up some notes, but I didn't get that far. Sure you can read. But I'm typing in pretty quick, I'll forget what to say. Start typing it in. If you go back to what we've done, we have independence for the discrete case. And in discrete case, this is independence of the population. And then the chi-square test just implements this, really. That's all it does. Okay. The expected frequencies are based on these probabilities, and you get them right out of the margins. So it's direct. Independence for discrete is direct from the definition. Okay. How about for continuous? Well, for continuous, you certainly can't go that route because they're all zero. It's my or dependent or anything. The probability of measurement is equal to a specific value if that's zero. So that's completely wrong. People do try to mimic it by making up categories, but that's what they're doing. They're just making up categories. If you make up different categories, you can get a much different test. I never liked those things. And I'm doing consulting, I tell people, no, you don't put continuous data in categories until you have to. So then what are we going to do? Well, we can't get independence directly, we sort of do it indirectly, and we try to measure something different. And we'll talk about two measurements, maybe three, but I don't think I'll talk about chemicals in class. But the two are Pearson's R and Spearman's R. I guess you say Pearson's R. Spearman's R. They measure different things, but oddly enough, you can test independence. Okay? And the first one we started talking about was Pearson, right? That was the baseball piece. So now X and Y continues. What's independence for that? Well, then you need the PDF or the distribution function, right? We'll talk a little bit about this at the beginning of the course. This will be the joint PDF. You know, it's enough volume. You could have a joint PDF in this room. The floor, this direction out here would be X, and this direction out here would be Y. And then the density is just like a big blanket over the floor, and then you have a region here like this table, and the probability of X and Y landing on this table was just the volume under the blanket over this table. So that's what a PDF is, and then but independence is equivalent to the factor. product of the marginal ones. Now, not only it factors, but expectation factors. And the one fact I need is that okay, that's the one factor. Okay. So I did we back into it as you see. Okay, so our first measure is we're after a linear relationship. So again, the data or those pairs, right? We talked about last time. X1, Y1, X2, you know, it's like the baseball data we had where X was height and Y was weight. And in that baseball, we had 59 data points. And then we did a scatter plot. And it certainly looked linear, right? It's not going to be deterministic. So, we're looking so we let linear. And then what you want to do is just draw on an X bar and Y bar. And then you can pick out the test statistic. And it'll work for linear cases if you just do that. That's positive. There's negative. There's a quadratic, but you're not at the end, you're in the middle. Quadratic. And then, of course, what's the most nonlinear thing? What's the most nonlinear figure? Circle, right? It's always turning. And then you'll see this will just work if we do it fast. So you might make a mistake on it, you don't know why. And you can see those lines work. Here you have the same number of counts in each quadrant. Okay. And then again, you go to the positive linear one. They're mostly in quadrants 1 and 3, right? 1 is the first one. Mostly in 1 and 3. Here they're mostly in 2 and 4. Here they're mostly in 1 and 3. So you're going to make a mistake here if you just do the correlation coefficient. And here they sort of cancel out. And here they definitely cancel. Now you can actually have a test statistic which counts the number of points in a quadrant. And once I worked on a method where the computer had to tell if it was random or not. It was a simulation study. So you cannot look at 10,000 data sets. All right? When the computer looked at them. And we actually used that quadrant. The data were messy. Correlation would be enough. But we just did quadrant counts with medians. Okay, we don't do that. We just take the product here. you take xi times xi minus x bar, this is center. You see, if they're in quadrant 1, it's positive times positive. If they're in quadrant 3, it's negative times negative. The other two quadrants will be, the product will be negative. So in 1, in the first situation here, the positives have it, the negatives have it. Okay, the positive has it. Here, neither. Here, neither. Right? So the product, then we just take the average. If you had 10,000 data points here, then you'd have 10,000 products. You don't need 10,000 statistics. You can just use the data if that's what you want to use. So we just take the average. That's measured correlation. We just take the average product. You can see if we really get fouled up. Now the problem with this, if you leave this alone, then if you want this to be large and you measured everything in feet, I can make it much bigger. I just multiply each x by 12 in each quadrant. So my measurement will be 144 times yours. So it's crazy. Right? So you don't want any units in your measurement. And an easy way to get that is just to divide by, in a sense, the standard deviation. Just don't have the ends. And that's Pearson's law. Okay. So there aren't any units. The units cancel out. Unitless. If you did that multiplication that I just talked about, it would cancel out. So you haven't changed anything. So if I do that transformation I just talked about, the picture won't change. If you don't look at the units on the plot, when you do it on Minitab or bar, you'll never see the difference. It'll be the same pattern. So the measurement should be exactly the same. If it was deterministic, it would be this occurs, actually it can only if all the points fall in a straight line. Probably seeing like this in practice, but not. You know, if the straight line is positive slope, then you will be plus 1. If it's negative slope, then you will be minus 1. Okay. And generally, the closer I'll just take the absolute values to 1. More than your relationship. Okay. I'm sure you've seen Pearson's before. Now, how about at the population? Let's go back to the population. We have this joint distribution that we talked about. What's this thing estimating? And it's you can see what it's estimating if you just put some 1/n's in here, right? Maybe this isn't clear, but this is going to be like mu's, right? This is variances. So this is not hard to see. It's going to be estimating this. Okay, we call this rho, we might call it Pearson's rho. It's the Greek R anyways, so it's not. And then I want to do one more thing. If you add some algebra, you can work this out. It will come out with this. This is like the shortcut formula for covariances, right? We might have talked about this in the first part of the course. Now we back into the test on independence. Formation of linear relationship, we're going to get back to independence because of why. This is all I'm interested in. And I meant to say this in the last lecture, this is like baseline, right? We have independence and dependence is what? Well, I know exactly what independence is. That's like baseline. There's no relationship. If I do any conditional probabilities, the probability of x given y will be the same as the probability of x. Y does not help you to predict x whatsoever. So this definition is like gold. I know this. And it does come down to that factor. In particular, you can get this with independence too. Well, if x and y are independent, then this factors into the product of the expectations, and the numerator is 0.
You have to move your paper up a bit. Okay.
Now here you have a theorem. The problem is you don't have if and only if in here. The converse is not necessarily true. But the contrapositive is always true. The contrapositive is the negation of the conclusion implies the negation of the hypothesis. So this is always true. So we test for rho equal to 0. If we reject H naught, then we conclude the alternative, rho is not equal to 0. Well, then you're forced to conclude that x and y are dependent. So it's like we back into this. We back into the test of the hypothesis. So this is what we test for rho. But the conclusion, if you reject, well, if you don't reject, then there's nothing to say. But if you reject, then this is what you would conclude. You conclude dependence at the 5% level, the 1% level, or the p value. Then you have to standardize R and relates to the t-test and regression we talk about, and that's usually the standardization people use. There's like 2 standardizations you can use. One is the t-ratio. the other ones. Would you compare this with T critical values? What you doing to solve degrees of freedom? When is this valid or exact? If X and Y are vibrating. The lamp that I talked about last just a while ago would be mound shaped, right? Picture. That's not how it is. Roberts. But if it's not vibrating normal, people still use a t-test. I don't know if I've ever seen anyone do anything else, except me. Under H0, you're squaring this, it's going to go away. Under H0, this should be close to 0. Well, then if you square it, it's going to be very close to 0. So you can sort of ignore it under H0. And then you have an asymptotic tendency. Then you compare this and see. Okay, any questions on Pearson's? I spent a lot of time on Pearson's because Spearman's is what? Suppose you were Frank Wilcox in the 30s. What would Frank do? He certainly didn't have a computer. He didn't have a calculator. He probably had a slide rule like I did. My grandson wants to know what a slide rule is. I'm supposed to bring my slide rule. I have it in my office. So what would Frank Wilcox do? Why do we have the Wilcoxon test? Frank Wilcoxon was a chemist, and he worked with numbers that had decimal points, like that, maybe 3 or 4 digits of accuracy. And he just like trying doing means and standard deviations. So we just ranked everything. And that's what Spearman's row would be. We'll just put the ranks. We'll write it down in a second. I meant to say, well, I'll say, what, it's just core of X. Now let's core, put the columns down. You can label the columns. And so then, how do we do Spearman's? We just put rank of X. That's Spearman's row. Just Spearman. Actually, that would predate Wilcox. Maybe that's where Wilcox has ideas. That's in Spearman. Now you're ranking from 1 to n, so the average rank is n plus 1 over 2. You don't have to do that. And you rank the x's and y's separately. And then you do it downstairs. I'll put it in. But if you think about it for a while, you could do these bottom sums in order, and then the rank would just be on. So it's like the ranks would disappear into a constant. So you don't have to do the bottom. Okay. That's Spearman's row, but it's just on the rank, so it's a correlation coefficient. It's between -1 and 1. Okay. Now what's measuring? You rank the x's and y's. It's not linear relationship. And for this, actually, if you want to do the finish this next time, but we can do the expected value. Sorry, I didn't do this for Spearman, so I'll talk about that in a moment. But don't use this formula. See, there's nothing in the bottom. That's just a constant. So the expectation is up here, right? And now do the expectation under H0. You get the denominator, you have this, expectations. So you do have this. But the x's and y's are independent under H0. Okay, H0 would be independence. The expectation of the product is the product of the expectations. Well, now you have the expected value of the rank of x of I, which is just n plus 1 over 2. It's 0. It's 0 times 0. So under independence, its expectation is 0. Okay. Then we can do the same thing we did with Pearson's. We'll just test for rho being 0. So we'll talk a little bit more about it next time. The problem is the correlate Pearson's comes out to a nice thing under the population and Spearman's doesn't. In fact, I won't even write it down in class. I'll give you a reference. But under independence, that thing will be 0. Okay, so we're on our, this is we'll have the final 15 minutes. You can even do some examples on this. The test is just this. You can do a t-test if you want to. We'll talk about that next time. You can just do the asymptotic one. Well, since we're done with it, just a few small things to talk about, and then we'll how would you do Spearman's and
Hold
just
on.
go to the rank first, rank them, rank the x's and y's separately, and then just ask for the correlation. Just click on 4. The mini-tab command would be in mini-tab, you can actually do it on the command line. I think you can do it just do that. They're doing C11. And C12 will be the rank of C2. And then I'll just ask for core. C11 and C12. These are my students. So I'll see you on. That's good.